So today we're going to start discussing crystal growth mechanisms in depth. Um, and I'm going to introduce some mechanistic concepts and give you a historical perspective on this. This is actually a very big area of science, and so we're just going to hit the highlights. So before we jump into that, a few concepts to review from last time. One is electrostatic stabilization of colloids is a very important and interesting area of study. We talked about how there's a potential associated with a charge distribution around the nanoparticle. And if the surface of the particle has adsorbed ions that are in excess, one charge in excess over the other, you get this potential that then dissipates into the solution, where you see a greater concentration of counterions, and then finally down to an electric potential of 0. And the magnitude of that potential at the slipping plane is what's known as the zeta potential, and that zeta potential value is something that can be measured by looking at how electric fields move particles around, because the slipping plane is what sticks to the particle when it moves. So that zeta potential value tells you something about how charged the object is, and therefore how likely it is to repel other particles that have the same kind of potential. And so zeta potentials better than 40 or 50 are where particles become stable in polar media. There are also steric stabilization modes and ligand binding modes that are really dependent upon achieving charge balance at the particle surface rather than this sort of distributed electrostatic situation. We talked about how different ligand types can be defined by how many electrons they bring to forming the bond between the metal atoms in the crystal, or the chalcogens or pnictogen atoms in the crystal, and the ligand binding element. And so X-type ligands are those that contribute 1 electron to form the bond. L-type ligands are neutral donors, standard Lewis bases like phosphines, for example, that contribute 2. And then we talked about how metal ions and their ligand anions can come on and off the particle, and we define those as Z-type or acceptor ligands. So each of those different classes was discussed last time, and we talked in depth about how the stoichiometry of the particle, in the case of cadmium selenide, say the cadmium and chalcogen ratio, dictate the numbers and types of ligands that are present on the surface of the particle. And we walked through a handful of different reactions that are summarized here at the top. There's an X-type exchange where chlorotrimethylsilane replaces carboxylate for chloride. And in this example, tributylphosphine binds to the product. So the carboxylate for chloride conversion is this X-type exchange. We also talked about the displacement of cadmium carboxylate using amine donors. And so that's removal of these Z-type ligands and binding of an L-type ligand. And we talked about the importance of forming ion pairs, particularly when there are acidic hydrogens around, and the difficulty distinguishing an ammonium carboxylate adsorbed to a particle surface and a cadmium carboxylate and an amine adsorbed. Differentiating between that hydrogen ion and the cadmium ion is very difficult to do, but possible. And then, of course, the more familiar, perhaps, L-type exchange reaction there on the bottom, one neutral donor for another. That's the sort of classic picture most people have in their minds for ligand exchanges and for stabilization of dispersions. But really, I think the reactions above that one are more important, in part because they're more likely to provide a stable dispersion. We showed how even some of the strongest binders with the best coverages produce samples that are relatively unstable to aggregation. All right, so let's change gears now. Oh yeah, one more thing. A very important principle in all of this is that the areal atomic density of surface atoms is actually really high on these binary crystals. Um, they're higher than the alkane chain packing density can allow. So, you can't put one alkane down for every surface atom on these materials. There's not enough space for all the hydrogen and carbon. And so this makes steric interactions between ligands on surfaces really important. And it means that the affinity of different molecules for a surface is strongly related to how many bonds can be made per organic spinach that comes along with the binder. And so that makes small molecules more useful ligands than large ones, or at least small molecules are more likely to have good coverages and high affinity than large ones for that reason. So a very important thing, broadly true, surface atom densities are higher than molecules can pack generally. All right, so we're going to change gears and start talking about synthesis methods. This is actually a slide Lou Bruce gave me years ago. Um, and, there are two parts about it that I like. One is the sort of standard synthetic setup there on the right of a cadmium selenide synthesis, I believe, because of the color in the bottom of that flask. These are vessels operated at 300 degrees Celsius under argon, organic solvents and surfactants at very high temperatures, pyrophoric reagents. And so those synthetic methods, development of those techniques led to samples like these lead selenide cubes on the left. And those are relatively large crystals there on the left. 12 nanometers is pretty big for little crystals of this particular class, this material type. And you can see that basically all of those crystals are the same size. There's a little bit of size dispersity or distribution in the size, and that distribution is about 5%. If you go in there with a microscope, you can measure that and show that that's the case. So, one of the things that has really always kind of struck me about this is that it's even possible to make samples like that. And in particular, something I have devoted myself to and my group has been working on for many years is a better understanding of why such narrow distributions form. So that's the main focus of our mechanistic discussion. What gives rise to size and size distribution control in these kinds of syntheses? So we'll talk about the underlying chemistry of how those reactions work and how that relates to size distribution. All right, so for historical perspective, here I've shown two, what I would say are seminal synthetic methods in nanoparticle synthesis, one of which is um, an early paper by Mike Steigerwald and Paul Alivisatos and Lou Bruce. Alivisatos was my postdoc advisor. Lou Bruce was Alivisatos' postdoc advisor, and Mike Steigerwald was a research scientist at Bell Labs together with Lewis and Alivisatos at the same time. And Mike came up with this inverse micelle method of making cadmium selenide quantum dots and cadmium sulfide also, where they took a surfactant, this sulfonated is that a malonic acid? I've forgotten. And mixed it with heptane and water in a ratio of about 1,000 to 3. So just a little bit of water. And those polar sodium sulfonate groups form droplets or bind to the surface of water droplets, leading to an inverse micelle, inside of which the cadmium perchlorate would be dissolved. So you make little reaction vessels inside of those surfactants, and then Mike with all of his knowledge of main group organometallic chemistry, added bis-trimethylsilyl selenide to that mixture to form a cadmium selenide crystallite inside. And then Mike used a further trick to replace all of the water and get rid of these surfactants and recover an organometallic quantum dot there shown on the right with phenyl groups around its outside that was somewhat soluble and could be studied by Lewis and Paul. So those were very early days. Only 5 years later, Munji Buwendi, who was a postdoc with Bruce and a contemporary of Steigerwald and Alivasatos, he started an independent career at MIT, and he and his students, David Norris and Chris Murray, came up with this very famous reaction. Dimethyl cadmium was mixed with phosphine selenide and injected into topo, or trioctyl phosphine oxide, which is a industrial surfactant used in mining operations to extract various elements and make them soluble in organic solution. And so this, at 350 degrees C, these two reagents reacted with one another explosively. And in the end, poof, a sample of quantum dots formed with excellent size dispersity. It turns out there's a long story here, but most of this chemistry was actually happening via impurities in the topo. And so the structure drawn on the right is fictitious. But this method, this high temperature explosive decomposition method, has really had a huge impact on the field. And this particular paper has been cited 10,000 times, largely because of the quality of the dispersion of the products and the flexibility in the size. Now, let's just, one more paper. This is slowly people realize that these impurities in trioctyl phosphine oxide were doing the job. One of them is this phosphonic acid molecule shown in the upper left, and phosphonic acids make a complex with cadmium that can also be formed by reaction with cadmium oxide and elimination of water. And those cadmium phosphonate, that cadmium phosphonate polymer product reacts with phosphine chalcogenides, and then leading to other crystal shapes in the case shown here, or spherical quantum dots not shown. And it was really Paul and a fellow named Xiaogong Peng that discovered this method of adding these phosphonic acids and preforming a metal carboxylate, or phosphonate complex to get more controlled reactivity. And again, it turned out that there were impurities in the phosphonic acids they had sourced, including ones with short chains like methyl and ethyl. And those short chains led to the production of rod-shaped crystals and branched crystals. And so there, it's often the case that reactions do something that is not anticipated by the operator, and that, a smart person looks at it and says, hey, what can we do with that? And in this particular case, these anisotropic shapes appeared, and in, again, very good monodispersity. I mean, all of those rods have about the same diameters, and in fact, they have very similar lengths. So this was a period of time from 1990 to about 2005 or something like that, where there was an explosion in interest in this material class because of the power of the synthetic methods and the uniformity of the products. All right, so let's take a look at a video of a sort of classical quantum dot synthesis. That flask is at 350 degrees Celsius, and the operator there is rapidly injecting cadmium and selenium into the pot. You get a puff of smoke, and then you start to see the color change. And this fellow's pulling out aliquots from the mixture with time, which cools them down, cools that aliquot down, stops the growth. And so he gets these sort of time points as the reaction is progressing, shown there. And you may have noticed that the flask is changing colors with time. And what you're seeing in those aliquots that you can see now, or in the flask, is that the particles are growing. And this kind of evolution in size can be tracked with your eyes. And in many cases, people will stop the conversion once the color gets to the point that they like, and by cooling the flask down generally. And that allows them to control the final size. And this gave rise to these wonderful images shown there on the right. So let's watch this again, particularly the early time. Look at how he starts moving real fast, moving this thing around, swinging that syringe. He misses, squirts it in there. There's an explosion and a very rapid color change. This is a really dangerous thing that he's doing. The reagents are quite toxic. The reaction is explosive. It's not reproducible. It's not scalable. Or I should say the reproducibility is low, particularly because the reagents being used are not controlled. The impurities present vary from batch to batch of the source material and give all kinds of variability. But really, the thing that struck me about this is how can you have such explosive reaction kinetics, uncontrolled kinetics, give rise to such beautiful size distributions. Okay, so let's talk about how that arises here. And we're gonna have to sort of step back and talk about crystal growth uh, thermodynamics first. So an important thing to know is that there is a barrier to nucleation of a new phase. When growing a crystal or forming a snowflake or a bubble or a droplet, um, you have to overcome surface tension. Surface tension is an energetic uh, quantity that tells you the amount of energy per unit area of a crystal or a droplet or a bubble, um, in excess of forming the same amount of material in the bulk. So what that means is, like, imagine you have a bulk crystal, and it has some heat of formation, and then you pull out a small crystallite of it, and suddenly you've got all this surface, and now you've broken bonds to form that surface, and so you have to pay a penalty, and the penalty you pay is related to how much surface area there is, and so the surface tension is a measure of that. Okay, it's the energy per unit area of a crystal in excess of forming the same amount of that material as though it were bulk. Okay, so making the first little pieces of a crystal forces you must pay the surface tension in order to nucleate that small unit. And then as it gets larger and larger, the surface area to volume ratio goes down, and that surface tension quantity goes down for the on a per unit basis. Okay, so there's something called the Gibbs-Thompson relationship that formalizes this kind of thing, and it's expressed here as a solubility of a crystal with a radius r, here on the left, and that's related to the bulk solubility of the material in some medium, and exponentially dependent on the surface tension and the radius. Okay, and so this expression basically says that the smaller the crystallite gets, the more soluble it becomes. And the speed at which that happens depends upon the surface tension. Something with a very high surface tension doesn't want to form as a small object, and so it becomes more and more soluble, more easily broken to pieces as that surface tension goes up. I guess I didn't label that here, but that's what this gamma is. The gamma is the surface tension. So when, crystals don't want to be very small, droplets don't want to be very small, bubbles don't want to be very small. Um, it costs you less energy to evaporate a small droplet than a big one. Okay, so that creates some sort of an energetic barrier that you must cross in order to form a new piece of a different phase. When undergoing a phase transition, you have to overcome that energy. And so people have broken out nucleation processes into a couple of different classes. Um, they're sort of uh, there are primary nucleation events and there are secondary nucleation events. People talk about having a surface of the same material. Say you're growing a crystal of glucose or something, and you have a large area facet. Starting the next plane of glucose atoms on the surface of that crystal can be discussed as an example of nucleation. That's called secondary nucleation, but primary nucleation is the main one that we're interested in. And there's nucleation from homogeneous solution, and then sometimes there's nucleation on another surface. And nucleation on another surface tends to be a lower energy process because that other surface will stabilize the surface of the new phase that you want to form and reduce the surface tension. So heterogeneous nucleation is very common in crystal growth. In fact, in classical crystal growth, like the growth of pharmaceutical crystals or the formation of ice in the upper atmosphere or in aqueous solution, almost all examples are heterogeneous. Okay, so heterogeneous nucleation really dominates the field of crystallization. Homogeneous nucleation is very unusual and quite difficult to study or observe. So most of the time, nucleation is heterogeneous. It happens on another surface because that other surface helps to lower the tension and stabilize the new phase. Okay, so free energy of making a crystallite is size dependent, and the crystals are less stable the smaller they are. Now, I'm going to walk you through a handful of different classes of crystal growth mechanisms to kind of prepare you for the discussion about homogeneous nucleation, because that's sort of the simplest. So I'm actually beginning with the most complicated first here to kind of get this out of the way and to illustrate that there are many different types of crystallizations, okay? One of which is metal oxide nucleation and growth. And this is something that has been studied for decades. And there are a bunch of different mechanisms that are defined based on how big the pieces are that are involved in the crystallization. Okay, so there's crystallizations that proceed via monomers, or these molecular building blocks here. There are crystallizations that proceed by assembling larger building blocks. And then there are crystallizations that proceed by assembling even larger building blocks. Okay, so here what's called the nanoslab is really just the attachment of relatively small crystallites into these aggregates. Here you have molecular species rearranging and forming a nice crystalline product. And here you have separate molecular entities, say metal ions and oxygen anions, that are reacting via molecular steps. Another very important thing illustrated here are these networks. So this circle, this gray blob, encircles a amorphous polymeric gel that are commonly formed when making oxides. These gels are sort of arrested assemblies of the building blocks. They're not crystalline, they're amorphous, and it's thought that in many cases, nucleation of the product crystalline phase actually occurs from within one of these gels. And there's a lot of voodoo in the formation of metal oxides as a result, because those gels do not have simple kinetic nor thermodynamic properties. So here's a mechanism where the crystallite is assembling on the surface of this gel and growing within the gel, and also borrowing from soluble units in the solution. Down here again, you have the gel phase in equilibrium with soluble units that grow in size with time, where the gel is just sort of a reserve of those units being liberated to the solution. And then finally, no gel, just large building blocks coming together. So all of these kinds of mechanisms are thought to be important in the formation of metal oxides. But an important thing to bear in mind here is that the nucleation process in this particular one yeah, seems to be a dominant source of nucleation in this material class, and it's a heterogeneous type of a mechanism. It's a rearrangement of a solid rather than a soluble thing undergoing nucleation. Here, soluble things undergo nucleation, and this heterogeneous piece does not really participate except by supplying units. Okay. Um, Another type of crystal growth mechanism is the formation of metals. Metals form by a two-step kind of a mechanism. Generally, it's thought that you have some kind of metal salt that undergoes some sort of a reduction reaction, for example, with dihydrogen, is shown here. And that leads to a nucleus of some kind, shown as this M0 sub N, and liberating HX in this case. Now, these types of materials, turns out that this metal 0 sub N actually can act as a catalyst for the consumption of hydrogen. And it turns out that these kinds of materials or metals generally will absorb dihydrogen and help convert the metal salt to the product. And so what this amounts to is a mechanism where the conversion of the starting metal salt is actually occurring on the surface of the particle. Okay, and so it's a surface catalyzed reduction, and it tends to be the case that this part of the reaction is faster than this. It's hard to do that homogeneous nucleation. It's relatively fast to deposit and reduce metal salts on the growing particle surface. Now, this kind of reaction occurring at the surface phenomenon is distinct from other kinds of mechanisms, and in particular the homogeneous mechanism that we're going to talk about for the rest of the class today. So I want to change gears here and show you a video. Okay, so, whoops. This is kind of a fun thing. I don't know if you've ever seen this done. But these guys are adding Mentos to Diet Coke, and they make these rockets. And I guess, I'm sharing this with you here to kind of provoke your imagination a little bit and to ask, why does this happen? Somebody want to take a second to try and describe what we just saw?
Is it all the carbonation like crashing out of the solution at once?
Yeah, so, you've got a 2 liter of Diet Coke, and all of a sudden, all of the CO2 is being released at once. But why is that happening when you add a Mento? Turns out there are all these other videos of people trying to add other stuff. pennies, salt, you know, rubber ducks, and nothing really happens. It's really only Mentos that makes that happen. What's going on there? How does this relate to the discussion so far? Or another question, why doesn't that happen when you just take the cap off?
Isn't it like the sugar, or I think there's like potassium benzoate on the shell of like the Mentos too. So when it gets added to the Coke, I think it takes less work to create those bubbles, and so it explodes rather than it just happening when you just open a Coke if you add a penny or salt.
Yeah, so that's the basic idea. I mean, I think, you know, what you're saying in different terms, is that the nucleation of bubbles in that 2 liter of Coke is very difficult. It doesn't really happen in homogeneous solution very quickly. And so, you know, you pour Coke into a glass and you can see bubbles forming on the wall of the glass. They don't really spontaneously form in solution. A flute of champagne is the same. You know, the bubbles steadily form from the bottom of the glass and they rise up the glass in a stream. So it's difficult to nucleate bubbles in homogeneous solution. The Mento makes that possible. You add the Mento and suddenly you can nucleate bubbles on the surface of that Mento very effectively. And there's something special about the structure of a Mento that makes that nucleation process rapid. You know, a piece of plastic won't do it, a penny won't do it. It's just the Mento. Now, you know, glass and pennies, and they will nucleate bubbles, but not as effectively. So that's a case where the surface is catalyzing the bubble formation. And it's much like the transition metal reduction case. The surface of the metal particle catalyzes the reduction of the metal salt to help deposit more. Um, so it's a nice example of how heterogeneous nucleation of bubbles is faster than homogeneous nucleation. And in that particular case, much, much faster. And much like the metal particle formation mechanism as well. Okay, so I now want to transition to talking about homogeneous mechanisms exclusively because they seem to be especially important in the formation of nanocrystals for reasons that are still not very well understood. But it's the mechanism that I think is understood the best at this point and maybe the simplest to understand. So a homogeneous nucleation and growth mechanism um, in the formation of these nanocrystals proceeds by a couple of different steps. And I've just shown an example synthesis here on the right of this cadmium phosphonate reacting with a phosphine chalcogenide in topo to form these rods. And to help kind of guide the discussion a little bit, on the left over here, you have this metal X and ER2, where ER2 is representative of this E double bond to phosphorus. And so in these mechanisms, what happens is that the metal complex reacts with the chalcogen molecule, producing two byproducts. One is a unit of the growing crystal, this metal chalcogenide unit, and then also some organic byproducts labeled as Rx in this particular case. And what this does is it slowly produces monomers in the solution or solutes that then begin to assemble into crystals. Okay, and so these reactions have this kind of monomer or solute generating mechanism in them where the molecules added react with each other at with some kind of conversion kinetics to make soluble units of the product. Those soluble units then have to undergo nucleation. and that nucleation occurs by some kind of an assembly mechanism to make a very small piece of this new material. And of course, we've been talking about how difficult that is. And then that piece, once you get over the hump to making that bubble or crystal, reacts with more solutes in the solution faster than it was formed, and growth takes place. So monomers adsorb to the crystallite as they're formed in homogeneous solution, rather than nucleating new crystals. And so those are kind of the prototypical kinds of mechanisms. And each of those mechanisms involve these soluble units. People refer to those units as monomers. I prefer the term solute because it's not clear that they're always monomeric. But the point is that the units, there's this currency of crystal growth. In the case of a metal chalcogenide like cadmium sulfide, you could imagine it would be kind of one cadmium and one sulfur, or maybe two of each or something like that. And shuttling those pieces around via the various pathways is what defines how these reactions happen. Now, there's another type of a mechanism that takes place in these sorts of reactions called Ostwald ripening. Ostwald ripening is a mechanism that I like to call growth by cannibalism. And in the case of a homogeneous mechanism, Ostwald ripening occurs by exchanging monomeric units via the solution. Okay, and this video that I've got playing down here in the lower right shows that. Occasionally you'll see two circles kind of fuse together to make a new one, but now at this stage there's very little fusion happening, and you can see some of those circles are getting larger and some of them are getting smaller, and basically they're trading monomers. And the average size is increasing and the number of crystallites is dropping at the same time. So this type of a process lowers the free energy because it actually reduces the total surface area of the mixture, just like and follows the kind of Gibbs-Thompson like description of the thermodynamics of crystal growth. A nice example of this kind of thing is the formation of ice on your ice cream. If you leave your ice cream in the freezer for too long, you open it up and you see that the water is separating as these ice crystals on the surface, and the ice cream doesn't taste as good. And in fact, to make really good ice cream, what you want to do is make the smallest possible ice crystals you can. And one of the best ways to do that is with liquid nitrogen, which is kind of a fun trick. And then over time, those ice crystals will grow by cannibalizing their neighbors, one water molecule at a time. So that's another important mechanism that occurs in these types of reactions. Again, here exchanging monomeric units. So let's talk a little bit about the energies involved in the nucleation process to help illustrate why this is interesting and why homogeneous nucleation is so difficult. So we're going to talk about the delta G for forming a precipitate and divide the quantities or the energies in forming that precipitate into surface and volume terms. Okay, so the surface term is the surface tension of the entire precipitate. Okay, and as we've been saying, it's generally a positive quantity, or it's unfavorable to make surface. And it's an interesting thing. It may not always be, and that gives rise to very different types of crystal growth situations. But in this particular case, and in most cases, the delta G for the surface is going to be a positive or unfavorable quantity. For a sphere, you can define that as the surface area times the surface tension of the object. And then there's the energy of forming the same amount, or the volume of the sphere that you're interested in. So the volume term is the energy released to form this quantity of material in bulk, so not considering the surface, okay? And, when a solution is supersaturated, there is a driving force for this precipitation to occur, ignoring surface terms. And so under those conditions, the delta G for the volume of the material will be negative or downhill, okay? At equilibrium, delta G is 0, where the solute concentration equals the bulk solubility. And then, if the solute concentration is below that, if it's undersaturated, it's actually uphill to precipitate material. All right. So you can define this delta G volume in terms of the volume of the spherical particle you're considering times what's called a supersaturation energy. And this is an energy expressed as the as the monomer concentration over the bulk solubility. So you can express this as a ratio, a supersaturation ratio, S here. And so the natural log of that ratio times the times kT gives you what's called the supersaturation energy. So this is a measurement of how much energy is built into the solution as it's supersaturated. And it's exponentially dependent on concentration. All right, so two terms, a surface tension term and a bulk volume precipitation term. And if you look at those two, you'll realize that one of them goes as r squared and the other one goes as r cubed. One of them is a positive quantity and one of them is a negative quantity. And the sum of those two quantities gives rise to this interesting relationship shown here on the right. So you can see the surface term going up as r squared, where here is this overall delta G for precipitation is shown in this solid line. The volume term shown here in this dashed line going down as r cubed. And the sum of those two at early times, you'll see that this curve is dominated by the surface. So for very small crystallites where the surface area is very high compared to the volume, the delta G for forming that little crystallite is defined by surface area. And then the bigger the crystal gets, the less surface is important compared to bulk, and this term begins to take over. And so you end up with this curve where you have a maximum in the delta G for forming small objects at a particular radius that is labeled R star on this graph here. Okay, and so this is a classical description of the barrier to nucleating a sphere, assuming a positive surface tension and and precipitation from supersaturated solution. Okay, so importantly, this peak maximum here at this particular value of R star is labeled as delta G critical. Critical will become more clear in just a moment, but it is, it's a representation of the barrier height. You start from no radius. As the particle gets bigger, the delta G goes up until you hit this important radius, and then it falls off a cliff. Okay, so any crystal or bubble that you make that is larger than this radius, it becomes very favorable to grow it. Any crystal or bubble smaller than that radius, it's actually favorable to dissolve it. So much has been made out of this sort of a depiction. Now, you can take this this study, what are the conditions at this peak maximum here, or where the delta G for precipitation versus radius, where the derivative of those two is equal to 0. So at R star, you can solve this equation and show that the R star is really defined by the ratio of the surface tension and the supersaturation energy. Okay, so as the surface tension goes up, the R star gets larger. As the supersaturation energy goes up, the R star gets smaller. And so you can actually pull out what the barrier height would be just based on those two terms. And you can see that the delta G is really sensitive to surface tension and to supersaturation. Okay, so the barrier height is strongly dependent on these energetic quantities. Now, here's a depiction of what that looks like in the case where we're just changing the supersaturation. So I've plotted several different of these curves here at different values of the supersaturation energy. The red curve being a high supersaturation condition and the blue curve being low supersaturation. Notice how the peak maximum goes up as the supersaturation goes down. And so basically, the way I like to remember this is that if you have a very strongly supersaturated solution, it has enough driving force to get over the hump earlier. And so you can pay more to make a less favorable nucleus under conditions of high supersaturation. So if the supersaturation is low, the crystallization is reluctant to form any crystal at all, and only the largest crystals become favorable. So it has a harder time making a nucleus, and only nuclei that happen to form that are large will survive. Okay. So there's a strong relationship here between the supersaturation and the barrier height, and that also depends upon the radius. Okay, so if you look at the kinetics of getting over a barrier of that kind, you can express these as the rate of nucleation, which is the change of the concentration of nuclei versus change in time. As an exponential that depends on this delta G crit. Okay, so the barrier height for forming one of these objects. We've already determined this delta G in terms of the surface tension and the supersaturation energy. And so if you plug that back in, you'll find that this barrier height looks like this. And if you then use that to determine J, put that into this equation here, you end up with this equation called the classical nucleation equation. And this J, this rate of forming a nucleus with time, then has this very extreme dependence on the supersaturation ratio and the surface tension, etc. Okay, and so this equation for the nucleation tells you that the kinetics of making nuclei are going to have a very strong concentration dependence on the solute. Okay, so if you plot this graphically, you get something that looks like this, where here we've plotted the rate of nucleation. This is positive. This is negative. So unfavorable to form nuclei with time, maybe even nuclei dissolving with time, versus the solute concentration. Okay, and basically there is this thing called a critical concentration, where once you get to that critical concentration, the nucleation kinetics take off very, very steeply. Okay, so this function, this nucleation equation, is really kind of a step function that depends upon this supersaturation ratio. Once you get beyond this so-called critical concentration, the kinetics for nucleation are thought to skyrocket. And to give you a sense of this, you can take the surface tension for water in the gas phase, which is pretty well known, and calculate what the nucleation kinetics would be. at a given value of supersaturation. And you can see here a huge variation in how fast nucleation occurs. Now, this is plotted as nucleation time, which is 1 over the rate. It's like the photoluminescence lifetime. So something that takes 10 to the 62 years is very small, or is very slow. Something that happens in a femtosecond or a few femtoseconds is very fast. And that the change in these kinetics is really happening over a very small change in concentration, factor of 5. So the very, very strong concentration dependence of the kinetics for nucleation is kind of one of the very interesting hallmarks of what's called classical nucleation theory. All right, so Chris Murray, Munji Bawendi, and many others have used this sort of a picture to think about how to make nanoparticles. They wanted to make nanoparticles that were small, and so they thought, I just need to drive my supersaturation up, and then I can nucleate a whole bunch of crystals all at once, and in the end have a small number. And so you watch this guy with the syringe, and I like he swings it at the flask and then misses, and it's because he's trying to jam it in there as fast as he can, and push that supersaturation energy up as quickly as possible. And that's all a product of this belief that getting the solute concentration as high as they possibly can would give rise to faster kinetics for nucleation and smaller crystal sizes. All right. So things are a little bit more complicated than that, but that kind of classical picture of how nuclei form still permeates our thinking in this area. It's certainly important in many areas of science. In nanocrystal science, it's not clear how important it is, and the longer I work on these problems, the less I think it's a dominant or a good description of how nanoparticles form. But it's certainly present in all of the literature on this topic. So let's take a step back now, and with that kind of perspective on how nucleation happens and the barriers involved, let's take a look at one of these reactions again. So it turns out in all of the syntheses that at least the homogeneous nucleation and growth syntheses that I'm familiar with, you have the starting materials, the metal salt and the chalcogen or pnictogen, what have you. And those two starting materials undergo a slow reaction to make solute. And then that solute actually goes on to assemble into nanocrystals. Okay, and you can think about these two steps, the one labeled slow and then the ones labeled fast. These are like separate phases of the reaction. The first phase can operate independently of the second phase. This reaction between these molecules is kind of like a reserve or reservoir of crystal monomers that has to be released by breakdown of the ER bonds, okay? And so in homogeneous nucleation and growth mechanisms, it's thought that this part of the reaction is slower than this part. And really the kinetics of growing the crystal are dictated by the conversion of this starting material. So this type of an arrangement leads to a situation like the one shown on the left, and this is a very famous plot that's attributed to Victor Lemaire, another faculty member from Columbia's chemistry department years ago. And so he was studying the formation of sulfur particles, colloidal sulfur with narrow size distribution. And he used this picture here to talk about the various stages of crystal growth. And so stage 1 is where the solute concentration actually increases with time. Perhaps in the case of our nanocrystal forming reactions, the solutes are produced by converting the starting materials into solute, and the slope of this line, the increase in the concentration, is dictated by those conversion kinetics. And eventually, the solute concentration exceeds the equilibrium solubility limit. So now you're in a supersaturated regime. And then eventually you hit this critical threshold where the nucleation rate is supposed to turn on very suddenly. And once you're at that concentration, any new monomers you make can't really raise the concentration much at all, and they're just going to go to the formation of any the formation of any nuclei. And then those nuclei eventually consume all of the solutes faster than they're made, and that pushes the solute concentration down. So once the solute concentration starts to drop, you get below this critical concentration limit and nucleation turns off. And then all of the crystallites consume solutes by growing, and eventually the precursor reaction runs out of steam. There's no more starting material left, no new solutes are made, and the mixture approaches the equilibrium monomer concentration. And then at that stage, Ostwald ripening can take over if it's going to happen. This should say 4 here. Ostwald ripening will grow the average size, kind of like this video of red droplets I showed you earlier. Now, Lemaire, he was riffing off of classical nucleation theory, which had been developed shortly before his time, and he sort of realized that in a temporal evolution like this one, if the burst of nucleation that occurs here is very strongly dependent on the solute concentration and has this step function like behavior, you're going to get many crystallites produced in a very short period of time. And then again, you drop below this threshold concentration, nucleation stops. And this type of a kinetic scenario can give rise to a narrow size distribution. So Lemaire is credited for having proposed that the width of the nucleation phase is what dictates the size distribution. And I often make the analogy to a horse race where all of the horses are let out of the gate at the same time. This is a common analogy used in polymer chemistry to talk about polymer molecular weights. Here, the horses are let out when the bell goes off, and they all run around the track together. And so Lemaire said, classical nucleation theory tells us that nucleation is going to occur in a burst, in a short period of time. All the horses are let out of the gate, and then they grow at about the same pace, and therefore they end up at about the same size. So this is really all postulated because it's quite difficult to study these kinds of reactions with the sort of temporal resolution you need to see this kind of phenomenon. But this picture is pervasive in the field, okay? And there are a few alternatives to this sort of a model. All right. So along comes another fellow named Tadao Sugimoto, and Sugimoto realized that these types of kinetics can actually depend upon how fast the monomer formation kinetics happen. Sugimoto taught us that reactions that are really rapid, that produce solute quickly, will have a tendency to make many more small particles. And if these kinetics are slow, then you make fewer particles that end up larger in size. And so this sort of is an intuitive concept, I think, if you're familiar with this nucleation barrier stuff. And it's the same kind of principle that Chris Murray and Munji Buendi were using to make quantum dots in the early days, trying to get an explosive reaction, drive up the solute concentration, rapidly produce many crystallites, and maintain them in a very small size using this kind of a concept. Sugimoto formalized this in a lot more depth and it did one of the few studies where someone had actually correlated the kinetics of the solute generation and the concentration of crystals. So he did this by studying silver chloride. And silver chloride, of course, very important material because it was used for photographic films. So all of the major film companies that were making films for cameras and movies, they had to grow beautifully monodispersed silver chloride and deposit them on glass, or suspend them in a polyvinyl acetate film, um, and use that as a light sensitive material for generating an image. So the crystallization of silver chloride was studied in great detail. Silver chloride is also convenient to study because you can monitor the concentration of silver and chloride ions in real time using electrodes. And so it becomes relatively straightforward to do kinetics on these kinds of reactions. And Sugimoto, he studied the effect of the rate of solute generation in one of these reactions on the extent of nucleation. Okay, and so in the upper left here, you can see the solute concentration expressed as a supersaturation ratio for 5 different reactions that have different kinetics. This is a slow precursor conversion or solute supply example, and this is a fast solute supply example. And so each of these 5 reactions, notice how they hit roughly the same value of the supersaturation here, despite the fact that there's an order of magnitude change or so in the relative rates of the solute generation. So Sugimoto took those examples, and then he went about calculating the number of crystallites that are nucleated in each case. And what he found is that the slope of the line, or the rate of solute generation near the tops of these curves here, was roughly proportional to the number of crystallites produced. So Q naught here is a measurement of the rate of solute generation during the nucleation phase. So this is a fast reaction, this is a slow reaction, and this fast reaction produces a higher concentration of crystallites at the end. Okay, and he found this straight line relationship. And Sugimoto then went on to develop what's called his nucleation mass balance model. So what Sugimoto said was that all of the solutes produced by a precursor conversion reaction, for example, either go to the growth of nuclei or to the formation of nuclei once you've hit this threshold concentration. At concentrations lower than the critical concentration, solutes can just go to supersaturation. But he said that's not important. Once nucleation happens, you're at this critical concentration, and so your solutes are either going to go to make nuclei or to grow them. And then once you drop below that critical concentration, nuclei no longer form, and you're just in the growth world. So he just modeled the very tippy top of these curves by assuming that all solutes either go to growing or making nuclei. And then he expressed the growth kinetics in terms of the number of crystallites present times the growth rate of each crystal. And he expressed the nucleus formation kinetics as the change in the number of crystals with time multiplied by the volume of the nucleus. And the sum of those two quantities was then equal to the solute supply. So here's our Q naught again, or the rate of solute generation, this time multiplied by molar volume. So this equation's units are actually expressed in terms of volume of material. So this equation can be solved in the limit that critical nucleation theory works, namely that the solute concentration really doesn't change during the nucleation event because all nuclei either form or grow, form new crystals or grow existing crystals and there's no fluctuation in the solute concentration. So if you assume the solute concentration remains fixed until nucleation ends, you can solve this equation, and you'll end up with the result that the final number of crystals is actually equal to the solute generation rate during nucleation divided by the growth rate during nucleation. So this equation is really important because it tells you that fast solute supply kinetics actually give you more particles, like is shown in the graph on the lower left. And it also tells you, maybe counterintuitively, that the growth kinetics are inversely related to the number. And so a way to think about this is that growth kinetics that are slow are going to give you more particles. And the reason is that there's a competition going on between these two processes during the nucleation phase. If the growth process is slow and doesn't compete for monomers, you're going to devote more of the monomers to forming new crystallites. And as the number of crystallites goes up and the consumption of solutes by the crystallites becomes more and more important, the total amount of monomer being consumed is going to be proportional to the number of crystals. Increasing the number of crystals makes solute consumption faster. And eventually it becomes fast enough that it outcompetes the generation rate, and then the concentration drops and the whole process shuts off. Okay, so nucleation continues until the crystals are great enough in number that the consumption of solutes outcompetes its supply and nucleation stops. Okay, so fast growth kinetics means you don't need very many crystals to outcompete the supply before the nucleation shuts off. But if your crystals don't want to grow, they're reluctant to add monomers, you need a lot of them in order to consume all of that solute supply. Okay, so it turns out that in these kinds of conditions that the nucleation rate is actually not that important. What's really important is the growth rate. The solution, the reaction mixture kind of sits there at the critical concentration, nucleating until you have enough to drive the concentration down. Okay, so the growth kinetics dominate and dictate how many crystallites you get at the end of the day. All right. So, this whole picture assumes this type of a threshold jump in nucleation rate, where the solute concentration only varies over a very narrow range, or basically not at all. And only under those conditions do you get this kind of proportionality. All right. So that's enough for today. I know that that's a lot to swallow. And so I'm going to sort of wrap it up there before picking it up again next time. But just a few conclusions. So crystals have a size-dependent free energy. Small ones are less stable. And that instability is described as resulting from surface energy. So the tension associated with dangling bonds at the surface of the crystal or the droplet. So fewer connections at the surface means you have to pay an energy penalty to make fewer connections. This gives rise to a nucleation barrier, and generally this is highest in homogeneous solution. And so things like dust or scratching glass can often generate a site for heterogeneous nucleation. And most crystallization processes in industry control the kinetics of nucleation by thinking about by modifying the concentration of stuff in the pot on which crystals can nucleate, either by breaking up existing crystals or adding seeds or whatever. There are many different mechanisms for crystal growth. Some are homogeneous, some are heterogeneous. And, I would say that there's as many mechanisms as there are materials or more. And so there's an awful lot to be learned here, and I would I would say, very limited intuition about how and why these reactions work the way they do. Oswald ripening is a pretty important reaction. Remember that it lowers the energy of a system by dropping the number of particles and growing the average size. And this reduces the surface area and reduces the overall surface energy. In the classical picture, nucleation critically depends on solute concentration, and this led Victor Lemaire to suggest that a very rapid burst of nucleus formation could give you the narrow size that people see in colloidal syntheses. And Sugimoto went a little further to show how the number of crystals depends upon the kinetics of the solute supply during that phase. And so this will set a good backdrop for some of the mechanistic work I want to show you out of my own group this next time, and how that relates to the size distribution. So I think